All right. So hello. Welcome back to the real world. Finally have a chance to talk to you in person. And I think it's great. It's really, have a difficulty trying to try to know your face, although it's still part of your face. So, and also just a reminder that I have an office hour this morning. I mean, every Tuesday morning from 9 to 10. That's office hour. And our TA, Naga, also holds an office hour. I think it's on Friday morning, 8 to 9. So if you have basically any types of questions regarding the lecture or about assignments, programming assignments, figuring notebooks, you can always jump into the office hour. Although I don't have I'm not planning to have an online session for office hours. It's hard to explain the mathematical details online using whiteboard or whatever. Yeah, so if you can make it to the office hour, then that'll be great. Or if you cannot make it, try to reach me by email and CC the PA's email as well. Yeah, our TA will have more time to dig into the code if it's the question that you have is about the coding, about Python or about Downbeat. Okay, so I think we are pretty much done with the logistic regression model. But today, at the end of the part for how to evaluate models, we will still touch a little bit about that. I think there's some parts about L2 regularization that we can use logistic regression as an example. Okay, so the topic today is about how to evaluate the models we have trained. Okay, so using our assignment as example, we have trained a logistic regression model to make a binary classification. Right, we can do a lot of 0, 1 predictions. Some are correct. Hopefully, the majority of those predictions are correct. Right, but we know that it's inevitable that the models can make mistakes. Okay. So today we will go through several metrics that help us define the performance of the model. We want to quantify, like how good the model is. So I think speaking of performance, one concept that's naturally jumping to our head is using something like accuracy. Like we use a number, use a percentage to say, hey, my model makes 80% of the case correct predictions. Okay. But that is kind of an ambiguous statement because you have, so in our simplest case, we have two classes to predict, positive or negative. Right? Like in the email, is it a spam or not? Spam and it's positive, now it's negative. Right? So what is that number, like the 80% number apply to? Does it mean that for 80% of the case, if there is a spam email like coming into your inbox, then you have 80% of the chance to catch it? Or like if it's a normal email, that 80% of the chance your model, your filter will recognize it's a normal. Okay. So that 80% of the chance, that accuracy should basically applies to any one of the classes that you are interested in. And things will be more complex when your model is doing something more. You have, for example, 10 animals to recognize, 20 different persons' face to recognize. Then how do you come up with a metric that basically can be applied to any of those classes? If the model can recognize my face very well, like 100% accuracy, then it doesn't mean that it necessarily works well on each one of your faces. Right? So we need kind of a more detailed, more comprehensive definition of performance. Right? What kind of performance? Right. So we will start with the simple binary classification task. Right. We will still look at the 0 or 1 prediction, and we will try to define. Hi guys, there are 2 students on Zoom. So we'll define some basic metrics, which we will call the point metrics, and then we will use those point metrics to define more balanced and more integrated metrics for model. Okay. All right, let's get started. Okay. So before that, we will spend a little time on how to prepare a data set and split the data set into train, development, or sometimes called validation and test sets. That is usually a common practice in setting up a machine learning project. And we already had some experience measuring the regression model. Our second assignment is for linear regression. And one of the tasks is to use the residual sum of squares, right, to measure how good your linear model is. So that's just a little mention here, which is different from the way that we'll use, from the metrics that we'll use for classification models, like logistic regression models, right? Because these are totally 2 different kinds of tasks. This one is for predicting a continuous value, while the classification is discrete. Okay. And lastly, we should talk about the overfitting issue and the technique that we introduce to mitigate or to prevent the overfitting. Okay. But this is really a complex issue. So the technique that we introduce is just one of the huge amount of ways to deal with overfitting. While the model is simple, like logistic regression models, this kind of regularization is kind of sufficient. But while we have built deeper and deeper models, then we will use a one chapter to deal with overfitting more systematically. So that's the first time we talked about overfitting seriously today. Okay. All right. So let's look at how do we split a data set. And of course, first of all, we want the majority of the data to be used for training. That is our purpose. And we have 100 data points. If we only use 10 of it to train a model, then that's not effective, not efficient. Right? We want the majority to be used for the training task. But we also want to pull out some part of the data, ensure that these part of data are not involved in training. In other words, we don't want the model, and by the way, the model is just a bunch of parameters, right? We don't want our models to be able to see these parts during training, so that in a later stage, our estimation or evaluation on the model is not that biased. Right? We want to use the parts that's hold out to evaluate the model. Right? So and so that we don't cheat. Right? We don't use the data points within the training set to evaluate model. Then that's cheating because the model already seeing that data already. Okay. And within within this holdout part, there's a split between developments and test sets. So that's a more fine-grained split, okay? But it's if it's before the era of deep learning, you know, we seldom talk about the data set. We just split the data set with training and test. Okay, that is kind of sufficient when your data is small and when your model is small. But once we are now using huge amount of data, big data, and deep neural networks, then this threefold split is getting more and more actually useful and popular. Okay, but it's definitely not a evenly distributed threefold. The vast majority is the training set. And actually the data set is just quite a bit, only a small part of the total training set. Yeah. So let's look at the common workflow. We will keep the model trained on the training parts, on the training set, which is the blue parts. And the green parts, the data sets, is the subset that we use to tell like how the model perform kind of during the training. Okay, so say we decide to train a model for 100 epochs. So one epoch means one complete going through of the whole training set, right? So probably after 10 epochs, we will use these green parts, the data set, and apply our model on that green parts on the data set to give us some performance, to give us some number, like what is the accuracy, what is the cost on the green part. So this data set is used more actively or used more frequently during the training. Okay, we kind of use it to monitor the whole training process, right? So that we have some ideas of how well the training is, whether it's going on the correct direction, whether the cost is decreasing, right? It'll be crazy if the cost goes up and we are not aware of it. Okay, so that would be really necessary during the training. Okay, and the test set, on the other hand, is not used during the training, but it's once the training is done. Say we decided to train a model for 100 epochs, and we will wait until 100 epochs are done, and then we use the test set to give us some final score, to give us some final report. Okay, and we claim or we believe that the report given by the test set is unbiased, because it's true that it's never seen before. It's never seen during the training. Okay. Even for the data set, it's kind of seen by the model during the training, right? Because every couple of epochs, we will let the model apply it on the data set. Right? So the model kind of is aware of the existence of the data set, but the model is never applied to test set before. Okay, so the score returned by the test set is more unbiased. Okay, so speaking of the proportions, if your data set is kind of small, say you have below 10K, 20K, maybe 50K examples, which is easy to handle by laptop computers, then I think the number like 60, 20, 20 or 70, 30 split. So for this 70 to 30 split, it doesn't consider a data set at all. So that is sometimes also acceptable because it's just not necessary, because whether using data set or not doesn't make a huge difference. Right? But it's a totally different story if we have a really big data set. Say we have millions of sentences, millions of images, right? Then in those cases, we would always like keep a small proportion, like around 1% or 2% or maybe 5% as the dev and the test set. Okay. Sometimes we can really use much smaller numbers. Right? Yeah, because in those cases, the data can be expensive. Say you want to train a really good model that recognizes human faces, you want to collect data first, collect data that is of high quality, and you want some human annotations. Like sometimes the faces are covered, right? Faces are covered by the hair, by part of their body, and you want the some human labor to annotate those data. So data sets that's well annotated is really expensive to get access to. So you want to make sure the majority of the data set actually can be used for the training. All right, so that's the typical numbers we use for splitting the data sets. All right, so for the regression models, we know that we can use the sum of squares or residual sum squares to measure the performance, which is exactly this formula indicates, right? For the linear regression, once we have some predicted values, we would just subtract it from the ground truth and raise to the power 2, which gives us some positive numbers. And if we sum up across all the data points, that's just the residual sum of squares. Yeah, you can always, of course, normalize by the total number of instances. And the first one, the L1 error, is just a different version of it, but we use absolute differences. Okay, I think that it's not that commonly used as L2, okay, but it's basically tells the same quantity. Okay, we want those numbers to be small. Right. So given a linear model, we want the errors to be as small as possible.
Excuse me, apologies for the interruption. Are you recording this class?
Yes. Yeah.
So were you able to get into the mic section?
I didn't find a mic.
Oh,
yeah. I'm using my own laptop for recording. So
that's fine.
I think it comes in words.
Okay.
Yeah.
So
maybe why I just very quickly check.
Yeah, if there's a mic, then oh, it's right here.
card. Oh, and Liz too.
Hello. Oh, sorry. Thank you.
Okay, so that would be what you do when you start your recording on each of the.
Yeah. So as long as I turn it on, the recording will start.
It starts automatically 1 minute before class and ends.
Okay. Yeah. Yeah. Thanks so much. Wonderful. Yeah, that's what we did, right? We use this formula to compute the residual sum of square. And what we did is to apply this measurement on the whole testing set. I don't remember the details. Maybe for our linear regression assignments, our data set is just a tiny data set, so it doesn't really matter how we split train and test, right? But in real world applications, that's something we really need to stick with. Okay. All right, so the focus today would be the metrics for classification models, right? A little bit review of the logistic regression model that we talked about. We will need to use a sigma function to be applied to this linear combination of your feature, which is the inputs, and the parameter W and D. Okay? So the outputs of this sigma function is the probability of your data points belongs to class 1. Okay. And we make predictions by using the threshold of 50%, 0.5 as the threshold. If your output is above this threshold, and we say it should belong to class 1. If it's below 0.5, then the prediction is 0. And we only have 1 or 0. I think that's a straightforward strategy. Right? So if we visualize it, let's put our threshold in between, in the middle, which is 0.5 threshold. On the left side, everything on the left side are predicted as 0. While everything on the right are predicted to be 1. And I also colored the data points here. The data points that are colored green are the ones that are actually 1, or its ground truth label is 1. The other gray, those red circles, those are the ones with ground truth 0. Okay, so you can see it's not a perfect prediction, right? There are some zeros that are predicted by 1 or predicted as 1, right? So that's a mistake, right? On the right, there's a 1 here, but it's really supposed to be on the right, but it's predicted as 0. So those are the mistakes. Okay? So our next step is to account for those mistakes. Like, how do we come up with a systematic way to measure the performance in this case? Okay. All right. So on the next page, we will further split those predictions into a view called computer matrix. Okay, it's a typical method that we can use for classification models. So in this 2x2 matrix, okay, if we look at the rows, the first row will be all the data points that have a positive label or positive ground truth. Okay, and the second row would be negative labels. And if we look at the columns, then the right column would be all the data points that are predicted as 1. Okay, so the y hat equals 1. And the left column here would be those predicted as 0. Okay, so there are 2 dimensions. The row dimension is the ground truth, and the column dimension is the prediction. So by these 2x2 separation of the space, then we can easily place our data points into each of those 4 regions. And assume that we have that many data points. And so in this case, if you look at the upper right cell, this one, there's 12 green points in here, which means there are 12 data points that have positive labels, and they are correctly predicted as positive. Okay, and the lower left, 11 data points that have negative labels, and they are also correctly correctly predicted as negative, right? So the upper right and the lower left, these are the good examples, right? But if you look at this one, it's a mistake. It's positive ground truth, right? But it's predicted as negative. That's a mistake. And here, the two green ones to the lower right, right? It's also a mistake. So now we can, given this computer matrix, we can give some names to the data points or to the numbers that exist in each cell. Okay. First one is called true positive, which is the lower upper right. And I think the name is self-explanatory because they are predicted as positive and they are indeed true positive, right? So that's what the name indicates. Well, we created something called true positive here and we put it in the cell. Remember, we'll need to use these numbers later. Okay. And second, true negative, right? Those are the negative data points that are truly predicted as negative. Cool. So next one, the false positive, right? These two, they belong to the second column. Their prediction is positive, but indeed they are not. So it's a false positive. And accordingly, the upper left, false negative. Okay. They really should be picked by the model, but which didn't happen. Right? So it's a false negative. There are different names for the false negative and the false positives. But I think it's sufficient to remember this to kind of symmetry names. Okay, so now it's come to the concept we are kind of familiar with, right? We always talk about accuracy. So in this case, we can define accuracy basically by looking at the total number of correctly predicted numbers. So this true positive is correct, is good, and the true negative is also good. So we just sum up these two values, 12 and 11 in this case, and divide it by the total number of data points. That's straightforward, right? We're going to keep our eye on the good examples, right? And compute the ratio of all the good examples over the total one. Yes.
Down to the left there, it says true as true positive and false negative, negative as true negative and false positive.
Yes.
Typo is that actually?
I think it's so this true means that the data points that have true ground truth.
Or wouldn't that be true positive and true negative?
No, the data points with ground truth equals 1 is all the green data points. Yeah. So if you think from the perspective of the green data points, part of it is correctly picked, which becomes true positive. And the remaining parts is actually the false negative. Yeah, so if you sum up these first rows, that's the total number of actual positive examples. And same story for the negative examples. While the majority of the negative examples are predicted as negative, the left, the remaining negative examples are incorrectly predicted as false positive. So if you sum up all those, the second row, it becomes the total number of negative examples. All right. Yeah, that is the accuracy. So let's return to the example that we gave at the beginning, right? When we talk about the model, the performance of your model, then when you claim you have 80% accuracy, now basically what you're assuming is that that accuracy applies to all the classes, each one of the classes that you consider, right? So it becomes really difficult if you want to handle multiple classes. If you want to build a model that recognize 1,000 types of objects, okay, then it's hard to keep that overall accuracy level around 80%. Right, so for that, you need to consider each class individually. Okay. Yeah, so accuracy is the first type of integrated measurement, right, that considers positive examples and negative ones. And actually, we can come up with more combinations. So on the next slide, we have a new term called precision. Okay. So precision, it considers these two cells, the second column, those data points that are predicted as positive. Okay, but these are not necessarily all good. These two, they are bad examples. They are false positives. So precision is defined as the ratio of true positives among all positive predictions. So sometimes it's also called true positive rate. Okay. So I think the name also explains, right? We want our model to predict precisely, right? So it's easy to build a model that always makes certain type of predictions, right? We can always predict that tomorrow is going to be sunny, right? And the precision may be high in San Diego, but not necessarily so in different city, different place, right? So it kind of measures like how precise your positive prediction is among all the predictions you have made. Okay, so this is something we want to keep in mind. Okay, sometimes when your precision is low, you will need to like pay extra costs. Okay. So later on, after we introduce recall, we'll see the difference. So interestingly, the second metric that we call the recall is defined over the first row, which is all the positive examples, all the data points that have positive label, positive branches. Okay, but since our model is not perfect, not all the positive examples are predicted as positive. Right? There is a false negative here. Okay, so the recall here is kind of the ratio of the correctly predicted positive examples among all the positive examples. Okay. So these false negatives, they are left behind. So in cases where we don't want to leave positive examples behind, we want to increase the recall, right? We want the model to make as many positive predictions as possible. Okay, but that will lead to the problem for the precision. Right? Remember in the previous slide, if we make as many positive predictions as possible, then our precision is going to be decrease. Right? So there's obviously a trade-off between the precision and recall. Okay. So if I make a prediction that tomorrow is going to be sunny, then indeed my recall will be really high because I will not miss any sunny day, right? But my precision is not that perfect, yeah. And it applies to different scenarios, different other cases. All right. So let's see. The last metric that we have, which is kind of a symmetric to recall. So recall is focused on positive ground truths, but for false positive rate at PR, we focus on the data points with negative ground truths. So if we look at the second row, and if we compute the ratio of these positive, false positive over the second row, in this case, it's around 0.15 something. This is the incorrectly predicted examples among all the negative ones. So it's if we use 1 minus 0.15 is 85, right? 85%. So this 85% is kind of the recall for negative examples. Okay, it's just symmetric to the recall of positive ones. Yeah, but in this binary classification model, we would usually focus on the detection of positive examples. Yeah, because that is how to say how we frame the problem. Like the task is to detect something, to detect the incidence of some events, to detect to diagnose the disease, for example, right? So it's kind of the positive results that we are more interested in. Okay, but for negative results, we can always also define a recall on it. But more commonly speaking, we will use 1 minus the recall on the negative results to give us the false positive rate. Okay, so this FPR is also something we can use in combination with the precision together. Okay. All right, so before that, let's look at a more integrated measurement called F1. Once we have all those numbers filled out, and if we utilize these 3 cells, it's kind of a combination of recall and precision, right? Of the 2 directions, right? If we use this precision times recall times 2 divided by the summation of precision and recall, which gives us a more balanced measurements of the performance. Okay. Because precision recall, these 2 parts, they are not it's hard to achieve a good scores for both at the same time. Okay, so there's a kind of a natural trade-offs between the 2. So we take something between them as a balanced measurement. Okay, so it makes it easier for you to write a report, right? When you say that your precision is 90%, you're kind of hiding some information about the recall, right? And when you, on the other hand, you say your recall reaches 80%, but actually your precision may be really low, something like that. Okay. So why not we just compute the kind of the average of these 2? Okay, so F1 is something we can use, and actually we use a lot if you want to like have a overall measurements about performance. All right. Precisionary recall. So here, let's use a formula to look at the trade-offs. Right. So look at precision on the left. It's defined on top of this and this, right? These two cells. So basically, it's true positive divided by true positive plus false positive. On the other hand, the recall is true positive divided by true positive plus false negative. So it's really the false negative and the false positive that determines whether your precision is going to increase or the recall is going to increase. So think about the problem. Think about the behaviors of the model. So if you want a model to be, for example, more conservative or more reluctant in making positive predictions, then your false positive would be lower because you discourage your model to make positive examples. Right? Say, for example, you can set a higher bar, like you only consider the logistic regression model that outputs 60 or above probabilities as a positive prediction. That's something you can do, right? But then, of course, will lower the false positive rate. Right? But on the other hand, your model is not maybe bold enough to pick up these actually positive examples. Right. So if your model is conservative, then more positive examples will leave here because it's never picked up to the right side. Okay, so it's an obvious trade-offs. Okay. There's no perfect solution to this. What we can do is just to find a balance, to find a point that we are both happy with the recall and the precision. Okay. So that's why people can use the plots. When we plot precision against recall, it's usually a decreasing trend at the end. When you are trying to push the recall to a high level, then inevitably your precision will drop. Okay, but before, when recall is below certain values, then the precision was basically very high. Okay, but usually we would we like to get the points over here or some point here that we are happy with the balanced measurements. Sometimes we just tolerate maybe 20% error or 15% error. That's totally fine. Okay. And it's a good way to compare models. Okay. So say in this example, we can have two versions of logistic regression. Right? The blue one is the plain logistic regression, and for the green curve, the orange curve, maybe we apply some L2 regularization, which we're gonna mention later. Maybe the green curve, the orange curves hit a higher position, right? Given the same recall, it has a higher precision. Right? And maybe look at this point. Okay, here is higher, and maybe here it's overlaps. Okay, so it makes it easy to make an overall comparison between models. right? You just look at the behaviors of models with at different levels of recall, different levels of precision. Okay. All right. So that's recall and precision. So we also define the false positive rate, right, which is the a different version of recall on negative examples. And that number is more commonly used in generating some curve called receiver operating characteristic, RC curve. And this curve is basically the true positive rate against false positive rate. And true positive rate is just the precision. Okay, so it's precision against false positive rate, PR. Okay, and this curve compared to the precision and recall curve is more stable. Okay, we'll see a later example on the next slide. And also it's quite interpretable. So we want the true quality rate to be high. We want 100% precision, right? But basically in practice, it's hard to achieve. Also, we want to keep the false positive rate low. So we want the model to be clustered around this upper left corner. This is the theoretical the perfect classifier. Okay, so we want the curve to be kind of as high as possible towards these theoretical best points. Okay. But usually we would end up with a curve that is lower. Okay. But that's a way to compare the models. If we have a blue curve, then we of course would prefer it over the green ones, the orange ones. And if it unfortunately drops here, then it's a terrible classification model. Okay. The paper is from 2006. The first time introduced the false positive rates against true positive rates. Yeah. So this type of model is a buggy one. Right? That's something terrible mistakes happen because it's worse than a random guess. Okay. Sometimes these ones are preferred. Okay. So if you compare the RC curve over the recall and precision curve. So remember, recall and precision curve is something that's decreasing, right? Something decreasing. The advantage is that RC curves are more stable to imbalanced classes. So when your data set has two classes, spam mail or not spam mail, so probably you only have 1,000 spam mail examples, but you have 20,000 the normal emails. So that makes your data set really imbalanced. And in those cases, the precision and recall may generate quite deviant patterns. Okay, maybe in a balanced data set, your precision and recall could be looks pretty normal, looks like a normal decreasing, but when it's becoming imbalanced, right, it becomes kind of hard to explain. Okay, so precision and recall plot is not as stable as RC. RC is always kind of a curve that's attracted by this upper left point. Right, it's always this curve. All you need to do is to calculate the region under the RC curve and always find the curve that has higher regions below the curve. Okay. So no matter how imbalanced the data set is, it's always kind of generates a stable pattern. All right. So that's for all the points metrics, right? We start from the confusion matrix by defining the true, positive, false, negative, all those four numbers, and then we use the combinations of those numbers to define precision recall, right? And then we can like extend these actually we can extend this to multiple classes accordingly. Okay. So nowadays we don't need to implement all the calculation ourselves. Just use packages like scikit-learn and tell that we have like 5 classes, right? And have that much of correct, incorrect predictions, and those numbers can be like automatically computed, right? And for the confusion matrix, the numbers we should maybe focus on that tell us the major performance is the diagonal lines, which are the correct predictions. And when you think about incorrect predictions, like you want to know, for example, so this is a result from the voice recognition. So when you have produced some vowel like I, and it's probably received into different vowels. So when you think about incorrect predictions, you need to consider more than one column. You need to consider all the remaining 4 columns as incorrect predictions. Right, that's for multiple classes. Okay, so next, I would like you to think about cases whether you want to prefer precision or recall. Okay, and the first case is if you are a doctor to diagnose brain tumor, to decide whether you want to conduct a surgery or not. Okay. The second example is to like detect explosive in the airport. Okay. Yeah, think about the questions. Maybe and try to explain your choices. Yes.
Let's say high precision for a brain tumor, or high recall for explosive.
Yeah, I think that makes sense. Because the cost you need to pay for false positive is just something you cannot afford, right? You want to make a surgery to find a patient, to cut out to find the tumor, right? So that's really some hard requirements on the high precisions. Okay, and for recall, for the second example, it doesn't pay too much if it's a false alarm, right? But you want to make sure that there's no suspects, no positive examples left behind. Right? So different kind of scenario decide what kind of metrics you want to use. Okay. All right, so let's talk about overfitting and the regularization here. All right, so overfitting occurs when our model fits the data too well. Okay, so that's just a qualitative statement. So it's kind of contradictory because we want to train a model that performs good, but sometimes we don't want it to be too good. Okay, so how do we define too good? So we will try to see if the model also works pretty well on new data. Okay, so if the model doesn't work that well, say we have a training set and test set, right? And we use a validation set to monitor the training process, and we keep an eye on the cost curve, and the cost could decrease during the training, right? And at a certain point, we stop here, and then we apply the model to a test set, and we almost for sure we will find that the cost on the test set will be higher than the training set. Right? So that is something kind of inevitable because no models can generalize 100% to new data. Right? But we want to keep the difference small. Right? We want the model that we train doesn't actually overfit too much to the training sets and maintain some capacities to generalize, to tell the general patterns. Okay. And we don't want the model to simply memorize the patterns in the training sets or to memorize the idiosyncrasies in the data. But we want something higher level to be discovered, something more general. Okay. So the causes, the two main causes for overfitting is that either you have too little data or your model is too complex. When you have too many parameters fitted on the small set, then it's very likely to cause overfitting, right? So say with these data points, if we use a simple quadratic function to fit it, right? Several parameters, right? It may be a good model, right? If we use higher order terms, to make sure that the curve that we fit has each data point exactly, then that's a very good model during training because if you measure the predicted value and the ground truth, the sum of squares is almost zero. Okay, but it's a terrible model given the new data sets, the new data points. Okay, so as a comparison, if we use too few parameters, then it's the so-called underfitting. Okay, we could have used more in this case. And actually, it's quite it's an empirical standard that we need to take. Right, sometimes the parameters that works well, the linear model that works pretty well on a different data set may not be enough. Right? In this case, we may need to use this quadratic function. But sometimes the quadratic function can also be insufficient. Okay, so it depends on the data and it depends on your choice of the model. Okay. And in just another example for classification models. So overfitting occurs when your model is trying to make a perfect prediction. It's trying to make all those crosses to the on one side, on all the circles on the other side of the decision boundary. Then that is sometimes a terrible choice because it overlooks the natural patterns of the two classes. Okay, so if we want to deal with the overfitting issue, so we might start from before we start training a model. When we decide the models, and we think about the data. Not all features of data are necessary or equally important, right? So it makes sense that we do some filtering work on the data side. Right? We want to select the good features, right? We may start off by including all the features and then gradually pick out some useless features or not that informative features. And all the features that are left will make a more concise model, a more informative model that's generalized as well. Okay, so that's at the feature selection stage. And for larger data sets and the more complex models, or to data sets that the features is not easy to get engineered, right? Which is typically true in deep learning. We will, like, for example, use the early stopping strategy. Right? We observe the training cost. It should always decrease, right? If it's ideal case. But sometimes your validation, your cost on the validation set may suddenly start to increase, because that's the point where overfitting occurs. Okay, so that's the point where you want to stop. Okay, I think that is a really straightforward technique. That's almost always true in natural language data, according to my experience. When you hold like 2% of the training set as a validation set, and you observe the training cost, it always decreases at the beginning, maybe 50 epochs, and then suddenly start to increase. And that's necessarily the point you want to stop. Okay. It almost always works for deep neural network models. Okay. And the third option is the one we will talk about today. It's called regularization term. Okay. An idea behind is that we want to place some constraints on the magnitude of our parameters. We don't want the parameters in our model grow too high. Okay. We want to set a limit to the parameters. Okay. So this is a easy to use and off-the-shelf solution, because we don't need to know anything about the feature. Okay. And sometimes we can also, but I would say that we should combine the second way and the third way, right? But really, we don't need to know too much about the feature if we use the regularization. Okay, so let's look at how it works. An idea is quite simple. So all the models we have talked about so far, linear regression, logistic regression, it's we all use gradient descent to solve it. And the idea behind gradient descent is that we want to minimize the cost function, right? So that's what we do. We minimize the cost of the model, which is just a theta or W and B, given our data sets. The data set is just X and Y's, right? So that's what we do when we use gradient descent to train a model, right? We want to minimize the cost. But now we made a modification to the equation. We want to minimize not just the cost, but also the complexity. Why? More complex models means higher chance or more likely to be overfitting. So we want to punish the complexity of the model. The complexity will be something we want to minimize at the same time with the cost. Okay, we don't want the complexity to grow too much. Okay. And how we measure the complexity is to use the so-called L2 regularization. Okay. And actually it's quite straightforward. The L2 regularization term is just the L2 norms of the parameters. Your parameter is W. W is a vector, right? It has n components, and you just use W1 squared plus W2 squared plus Wn squared. The summation of all your components in your parameter is the so-called L2 regularization term. And you put that term to sum up with the cost function, and you minimize the cost and the L2 simultaneously. That is how to do the L2 regularization technique. Okay, so for linear regression, right? That's our old cost function, right? Summation of square of differences. That's our old cost function. If we don't have this part, then it's just a pure linear regression, right? But now we add this term. The W transpose times W itself is just the inner product, okay? An inner product of the vector itself, which is how you compute W1 square plus W2 square and so on, right? And we use the lambda to control the strength of the regularization. So lambda is a constant, something you can decide. It's just like the learning rate. Okay, if we use a large number, then we place very hard regularization on W, and it may not be good. So it's something we need to try. Okay, so with this new cost function, once we take the derivatives of it with respect to W, for example, then this term becomes this linear term, right? After we take the derivatives off, and the gradients would become a new, slightly different form, right? We have this new form because there's a new term in the gradients. Okay? And if we look at it, we can see that in gradient descent, when we compare the regularized gradients with the non-regularized, the difference is that we use alpha times lambda divided by n to play some penalty to W. If you say, imagine if lambda equals 0, then this term becomes 1 minus 0, which is just W, which is exactly the same as the old gradient descent. Okay? But if lambda is positive number, then this term becomes a smaller W. Because it's 1 minus something positive. Okay? And the consequence is that if you use a positive lambda, then our W becomes smaller than usual, smaller than before. And smaller W means that's a simpler model learned, not that complex model learned. And similarly, we can apply the regularization to logistic regression. Because the cost function is similar form, and we have an additional term here, and we take the derivative of the additional term in the gradient descent will be here. It's the same outcome as the linear regression. Okay. So L2 regularization is really straightforward to implement, and nowadays when we use machine learning packages, we don't need to do that manually. Okay, we just tell the optimizer that we want to use some L2 regularization and how strong the regularization should be. Okay. So when we use lambda to control the strength of L2 regularization, if we use lambda equals 1, for example, then it's too hard. Right? Lambda becomes a very big number, then the nonlinear models that should have been learned becomes a linear one. So it's a huge loss of information, and the model probably not gonna work. Okay. And if lambda is too low, then it's just a no regularization. Okay, so overfitting still could be an issue. So it's a quite model dependence and data dependence issue. Something you wanna experiment in your studies. Okay. So I think we have several minutes. Let's see if we can run this example here. Let me end the show. It's a beautiful visualization tool provided by the Google developers. So different kinds of models we can use for different types of problems. So the task here is to separate the two clusters, and we can use L2 and use here to control the L2 regularization. Okay, so let's see. First of all, no L2 regularization. Learning rate default 0 hidden. Let's increase the hidden size. How do we do that? Let's try that. Test loss. So you see the test loss is increasing, right? After decrease sharply, then start to increasing because we are training the model too hard. Right? So let's see if we can add some L2. Let's start over. Let's put some great L2s here. So the testing loss, you see, it's suppressed. It's suppressed. Right? The test loss, if you look at the solid line, doesn't increase at all. Right? But the result is also just a linear model. Because that's our regularization to be very hard. The lambda is 0.1. And all the W's, all the parameters become very small, so that there's only a linear model left. Okay, so that's the price. Okay, when you want to a simple model, then the model doesn't do much, and when you train a complex model, the model may overfit. Somewhere between you can use the lambda to control basically how nonlinear a model is. Okay. So this is an example that you can play with at home with different setups. Okay. So that's so much for today. And in the logistic regression assignments, the last task asks you to compute the true policy, false policy, and a bunch of precision reasoning, right? So that's something I didn't cover last time, but now since this chapter is covered, then you can start working on it. Okay. An announcement I want to make for Thursday, there will be no class meeting because we have candidates visiting the departments. So I'm going to upload a video on a new chapter, a new topic on principal components analysis, and that will be the next chapter. Okay, for Thursday. So no class here on Thursday. Okay. Any questions? Let me know by email. All right. Thank you.
Thank you, Professor.
Yeah. Thank you.